Okay, so the social planner has to be able to predict the beliefs of the participants in the game in order to implement C. So the social planner has to know how the recipients of ideas are behaving in order to implement C. So the first thing he has to know is what they believe about each other when they're solving their decision problem, whether to bank an idea or to invest. Okay, so first of all, in order to implement C, it has to be the case that all of the recipients of ideas are behaving according to the same behavior. And that's a tricky business because what they know is different when they've received an idea from what they know when they haven't received an idea. So if you receive an idea, you've received it. Nobody knows that you've received it. The planner doesn't know, but neither do your competitors know that you've received the idea. So what you believe when you receive an idea is different. And if you're putting the idea in your pocket, but now time is passing, you have an idea in your pocket, and other people are receiving ideas. Indeed, you might have two ideas in your pocket. What does that do to your beliefs? Now, so I've gotten rid of this with the continuum, this problem, but actually we give a limit argument justifying this, so it's not as bad as it sounds. Nevertheless, what your beliefs are when you have an idea in your pocket will be different than the beliefs of somebody who doesn't have an idea in his pocket. This turns out not to matter, because by the time an investment decision must be made, the only people making those decisions are people with ideas in their pocket. Either you received the idea 10 days ago or you received it just now, but you still received an idea. And it turns out that the beliefs that you have conditional on having received an idea doesn't depend on when you received it. So that's a little bit odd as well. Okay, so all of these recipients have to be believing in the same and behaving according to the same cost function, and they have to know that the other agents are also behaving according to this cost function, because that's what allows them to update their beliefs on the lambda in a way that's internally consistent and the same for all of them. So it turns out the innovator's function then as a profit, the innovator's profit then as a function of time is the following. So the innovator has an idea, the potential innovator has an idea, the idea recipient. The cost of that idea is, for example, C0. So remember that this C is not a cost, it's a cost function. It's the threshold function, the C over here that we're conditioning on. Why is it there? That's the threshold function that's being implemented, the one that the other recipients of ideas believe in. They believe it's being implemented. Okay, it's a function. But this cost is the cost that our potential innovator has right now, C0. It's an actual number. Okay, his decision, he has a decision right now at time t, whether he just received the idea or whether the idea is in his pocket. Same decision. He arrives at t, he has an idea, it doesn't matter when he got it. Okay, at time t, he has to decide at what time in the future would he be willing to invest, conditional on nobody investing before then. So his profit of waiting until t hat is this. This is the discounting. This is the probability. This probability function, of course, has to account for the updating on lambda and so on. This is the probability of arriving now at t hat in the future, starting from t, having arrived at t. This is the probability of arriving at t hat, having started at t. And this is the profit he receives if, in fact, he manages to escape all the possible preempting rivals until t hat. He will receive the reward that's available at t hat, net of his cost. Okay, and then because of the discounting, this is what he wants to maximize. So that's the profit he gets times the discounting times the probability that he actually gets there. So he's not going to wait forever because the probability of getting there, if he waits forever, is very small. What is the optimal investment decision then? So for each t hat, so his investment decision at each t hat is to invest if the rate at which, remember that his willingness to bank depends on the reward going up. If the reward isn't going up, he's certainly not going, if it's not going up anywhere in the future, he's certainly not going to invest. So he makes a local decision, which turns out to be the global decision. he will delay if the reward is going up faster than the opportunity cost. So here's the opportunity cost. What he's giving up at t hat is, this is the profit, the bracket over on the right is the profit that he would get if he invested today. If he delays for a small period of time dt, he loses the interest on that profit, that's the r. And he loses the possibility of being preempted by somebody else. So that's the expected, this is the expected hit rate in that period. This isn't obvious, by the way, because if you just wrote down the expected hit rate, it wouldn't look like this. This isn't entirely obvious, this form, but it's very intuitive. It's not obvious, but it is intuitive, if you'll permit me that. So this is the probability of being preempted in the period of time where he's collecting this, where he's giving up this rate of return on the profit. So if the opportunity cost is greater than the rate at which the reward is increasing, he will invest, and otherwise he won't. And notice that if you set these two things equal, there you have a differential equation, and that suggests that you can implement the optimal cost threshold by solving the differential equation. Okay, so you want to put the C of t here, where the C0 is, set the two things equal, and then you have a differential equation. And so you have the C of, remember, you have the C of t. What you want to do is implement the C of t, which the planner, the cost threshold, which the planner has derived to be optimal. And now we're asking, what is his choice function? His choice function is the reward function rho. So we're asking, can he find a function rho which will set these two things equal when you have here the C of t at each t? And if you think about that for 20 seconds or less, you will see that that's a differential equation, a first degree differential equation to which there ought to be a solution, and indeed there is a solution. And it's a very ugly solution, which I haven't written down for you on these slides. But the theorem says that it says what the solution is, which is some ugly solution to a differential equation. But the important part is that this reward function exists, that it does satisfy the property that we derived intuitively. The reward always now has to be larger than the cost to avoid the banking, to avoid excess banking. You want them to be doing some banking. You just want them to be doing not too much banking. And so, you know, what this reward function does is it mediates between getting them to bank, you know, high cost ideas, but not to bank very low cost ideas. And the other part of the characterization is that, in fact, the reward does converge to the cost as time goes on. So as t goes to infinity, the reward and the cost do, in fact, converge. So the reward function is increasing like the cost function. It's above the cost function, but it falls off. It doesn't increase as fast as the cost function in the limit. Okay, so I just want to come back. I actually don't think that the details of this model are the interesting. If there's an interesting part of this paper or of this line of thinking, it's not actually this model so much, maybe. But rather, what this model suggests, I think, as a way of thinking about innovative environments.